seminar of 2025. Today we will have Satej Soman speaking. Satej has been a visiting researcher over at AI for Good, and I'll let him take it away and give the rest of his intro. Satej.
Thanks so much, Stephanie. Thanks to you and Millicent for organizing this. I'm pretty excited to talk about what I've been building for the last 5-6 months now. Like Stephanie said, my name is Satej Soman, and I'll be talking about a system that we're calling Anaximander, which is a way to interactively orchestrate and evaluate geospatial foundation models. So as a little bit more of an intro, I'm currently a PhD student at UC Berkeley. My research focuses on using satellite imagery and digital traces to make better policymaking decisions. And the domains I usually work in are things like humanitarian aid targeting, economic development, or studying urbanization. For the last 5 or 6 months, though, I've been here in Nairobi as a visiting scientist with the AI for Good lab. And this is a research team at Microsoft that uses machine learning tools and modeling techniques and applies them to a number of kind of social impact domains. So things that the lab has worked on include rapid disaster relief, mapping out global building footprints, biodiversity monitoring, and food security early warning systems. And a common task across both these buckets of domains is to quickly and ideally interactively evaluate how different machine learning models trained on satellite imagery or remotely sensed data in general perform in problem or location specific contexts. So to help address that task, we built this system that we're calling Anaximander, and it's named after this ancient Greek philosopher who was believed to be the first person to try to map out the entire known world at the time. And it's a graphical user interface for evaluating these computer vision or geospatial models that supports quickly loading a model definition, specifying what data to pass to the model, defining where computation should occur, and inspecting model outputs in context. And just to give you a better idea of what these inputs and outputs are, here's an example piece of satellite imagery. So this is an aerial image taken of somewhere in rural Kenya. And you can see that largely the ground is bare, not built up, but you can see some buildings and some vegetation. And what you might want to get a machine learning model to do is do something like semantic segmentation, where each pixel in the image is assigned to a semantic class. So you might have bare ground, you might have built up areas, you might have roads, but you've created a semantic mask of the image based on a couple of classes. Or you might want to be a little more specific and do object detection, where each of the buildings in this case, that's the class that we care about, their bounds are delineated in the image. And finally, you might just want to run the image through an existing deep learning model and use that as a feature extractor backbone for a downstream task. But you might want to visualize or look at what the feature representation is of your input images. So with that super high level background, I'll spend the rest of the talk talking a little bit, fleshing out a bit of our motivation for building the system and how it compares with previous work. I'll give you a demonstration of the system's capabilities and the architecture that lets it do what it's capable of. And then I'll finish the talk with a case study of how we're starting in a preliminary way to use it for an ongoing food security project before wrapping up with challenges and future work. So if I could sum up the kind of like the core motivation behind a lot of these similar systems, I would say that evaluating a generic vision model is qualitatively different than evaluating a geospatial foundation model. And what I mean by that is, let's take this example here. Say I give this image of a giraffe to a vision classifier, and it spits out the prediction that, oh, this is an image of a submarine. I don't have to pull in any other data to understand that this is a category error, right? Like, just from what the model sees and comparing it to the model output, that's all I need to know to evaluate this particular prediction. Now, if I contrast that with something like a satellite image that I've given to a classifier, and it says that this is cropland. Now, if I just look at what the model is seeing and what it's making a prediction on, I'm a little suspicious of it. But just from what the model sees, I don't have enough context to say that this isn't cropland. Maybe it is actually cropland, but this particular image was taken by a satellite when it was in the dry season or there was a drought, or there are like particular satellite specific settings that make something that's like wheat or barley look like desert. So if I actually go back to where this particular image was sourced from and zoom out to see kind of what the surrounding regions are, then I can see that, oh, that satellite image was taken in Western Egypt, which is known to be desert. And once I have that context, then I can evaluate the prediction. And I have a lot more confidence once I source that additional context in saying that this is also category error. And evaluating geospatial models more broadly, going from like item level descriptions to kind of understanding the performance of that requires sourcing this additional context in a lot of ways. And this is also like how you would see if it's generalizing. If say, for example, you have a model that does really well on location A, and you want to see how well it does on location B. You have to go and source additional context and data apart from the training data to see how it's doing there. Or you might have a model that does really well because it's trained on high resolution satellite imagery taken at exactly the most opportune time. But at prediction time or inference time, you might only have access to low resolution imagery that's taken at a very different time in a very different context, especially like in a different part of the crop calendar for agricultural mapping. So you could absolutely do this evaluation purely in code. And if you're doing maybe like a non-geospatial machine learning pipeline, you probably are doing a large part of your evaluations purely in a code-driven setup. But what I hope the visuals and the animations that I've put together here suggest that a maybe more natural way of like expressing these manipulations of input data or scale or location is that this is almost tactile, and a graphical user interface might be a better way to express these kinds of transformations and evaluations. In fact, most geospatial data scientists and a lot of geospatial-driven data domain experts, a lot of their work happens in kind of these GUIs called geographic information systems, or GISs. And a really common one here is known as QGIS. So this is me playing around with the GPS coordinates of a couple of agricultural measurements. Let's see if I can get this to play. So each of these dots that you see are a GPS coordinate that was collected in the field by different organizations. And I'm overlaying that data with not just map imagery that is sourced from OpenStreetMap, but actual satellite imagery that's sourced from Google Maps. And I'm panning, I'm scaling, I'm zooming to different parts of the area of interest. In a second, you'll see me drag and drop additional data to see how it matches up with existing data that I have. And this is kind of I could do this all in a code-based manner, but these kinds of manipulations and explorations of the data, even if you're not necessarily evaluating a machine learning model, is just a way more natural way to deal with this kind of data modality. And that's what we're trying to build or bring to this kind of fluency is what we're trying to build to the geospatial machine learning model evaluation question. Now, like I mentioned, a lot of people who work in these kinds of ML evaluation workflows, all their work is pretty code, right? Like you'd import PyTorch, you'd set up some data loaders, you try to find some aspects of your data that you split it up with to understand how it's doing on different subsets. But a lot of the people who work in, like I said, a lot of the people who work in either like the domains that we're applying ML to, or are just GIS savvy in general, a lot of their work is GUI heavy. So this is kind of the gap that we're trying to bridge. And we're not really the first people to try to identify or try to bridge this gap. So out there, you actually have a couple of different existing GUI tools that try to target different users in this GUI savvy versus ML savvy kind of breakdown. So in one quadrant where you have tools that are for people that are neither really GIS savvy nor ML savvy, you have things like ChatGPT for maps. So there's geospatial reasoning from Google, there's Queryable Earth and Earth Copilot from Microsoft. And these are tools that allow you to use a chatbot interface to interact with data. A lot of the things that we should compare the tool that we built into are more in this kind of upper half where like people who understand the data pretty well and know how to do the manipulations. And a lot of them are building on top of the same GIS workflows that are GIS-based like QGIS, which I showed you. But sometimes they're either constrained to a single model. So if you want to swap out the model, the tool doesn't allow you to do that. Or they force you to run computation on this exact same server that you're running QGIS on, which is also a constraint that might not, that doesn't necessarily make sense as a binding constraint. So a lot of the tools are in And like we're not even like the first people at Microsoft to like kind of look at this. So other things from like AI for Good specifically include Torch Geo, which is an extension to Torch Vision specifically for GIS. But that's again a completely code library. There's no visualization here. And then other tools you have that involve a geospatial embedding explorer called SIMS that was developed by one of the scientists in the AI for Good lab, or a building damage assessment tool called HASTE, which uses a machine learning model behind the scenes. But all the machine learning stuff is kind of abstracted away from the end user who understands how and why it's being deployed in a certain geospatial context, right? So a lot of that is so a lot of the existing tools are focused on this upper quadrant, which is like people who are pretty good at GIS work and they understand the opportunities for building or bringing machine learning workflows into their work, but they don't really want to engage with selecting a model or figuring out how to deploy it or figuring out what the inputs are. That being said, so that's kind of the quadrant I just described. That being said, I think there's a lot of an opportunity to build tools for people who are both pretty ML savvy and pretty GIS savvy. And a lot of the workflows and domains that I mentioned at the beginning of the talk kind of fall into this area. So building new food security maps or upgrading the backbone of the user-facing tool to figure out what a better machine learning model for building damage detection is, or just evaluating new biodiversity models. Those require both a lot of ML savviness and a lot of GIS savviness, but there's very little tooling in this space. So this is kind of the quadrant that our tool tries to actually target. So our tool is built on top of QGIS. Again, it's like a very popular framework for doing a lot of GIS. It's free and open source, and most importantly, it's extensible via Python coded plugins. So I'm going to move on to a demo of the tool in action, and as kind of the motivating example, or like the example I'll return to, is segmenting the satellite image. So this is an image of agricultural fields, like farms out in rural South Africa. And when I say I want to segment this image, I want to find the bounds of each of these individual agricultural parcels so that I can understand things like what's the average farm size. I can start to see like how productive each individual parcel is. I can see if like land use patterns are changing. So it's a pretty common task in kind of satellite imagery analysis to actually want to delineate the fields in an agricultural setting. So I know that there are a lot of models out there. Want to keep it easy? Let's ask ChatGPT. So I created a prompt that tells ChatGPT to pretend it's an instant segmentation model. And I gave it all this context about what I want the final segmentation map to look like. And here you can see our tool will allow us to actually call the GPT image one endpoint using data from our viewport here in QGIS, plus the custom prompt that I just showed you on the last slide. So here I'm creating a new UI element. I'm pasting the prompt that I want to send to GPT-1. And what the tool is doing in the back end is taking the image from the viewport, sending it to GPT image 1 along with that prompt, and then georeferencing the data that it gets back and putting it, overlaying it on the map itself. Okay, so this is its attempt at trying to do some segmentation, and it doesn't look great. But so clearly, I would say like GPT image 1 in its training data has some sort of context of what a segmentation map should look like. And back there, I was like toggling between the input and output layers, and like this shape, it kind of gets right. It kind of gets like the overall shapes and kind of where they should be right. But if you need pixel perfect segmentation, this is not something you can actually rely on. So let's go pull a model that actually does segmentation. And just recently, Meta released a model called Segment Anything 3, which allows you to do all kinds of really cool like geometry or text-driven segmentation of both still images and videos. And the cool thing is that it's on Hugging Face. So we can tell our plugin to go search Hugging Face. So here, again, instead of going to like the ChatGPT sub part of the plugin, I'm going to a Hugging Face search interface. I'm searching for SAM3, and it's bringing up that entire family of models. I'm going to take the kind of the base generic one. And what I'm doing here is that I'm telling the plugin that I want to run it on like the satellite imagery that we're looking at. But what I've selected as the provider is the URL of a companion server that's running on a compute cluster that's enabled with GPUs. So what's going to happen when I click run inference is what's going to happen when I click run inference is that the model's going to, or the server is going to download the model from Hugging Face. And then the client here, the actual plugin, is going to tile up my data and send it to the model. And then the model send it to the server. And then the server is going to send the inference results back. So everything that's happened that could happen computation-wise, instead of happening on my CPU, is happening on a pretty beefy compute cluster, which would allow this to actually be somewhat interactive. So right now what you're seeing is that the model's been downloaded to our compute cluster, inference is running, and here we actually get some inference results back. So two things. First is, compared to the ChatGPT results, this is also already a huge improvement. So you can see kind of it gets the edge of this field, which is delineated from other fields by this road. It kind of gets this corner right. Some of the smaller fields it's starting to pick up on. But out of the box, this isn't a useful segmentation model. So what you could do is that you can start playing around with like different prompting strategies for this family of models and seeing what's going on there. But out of the box, like when you try to apply these generic vision models to specifically Earth observation data, this is not an atypical result. Like you'll get something that looks better than GPT image 1, but out of the box, it's super usable. And I think there's kind of a forking path here. Like maybe you start playing around with the geometry-driven prompts that segment anything here supports. Or you can be like, okay, I know this is a generic image model. What if I source a model that's specifically trained on satellite imagery? And that's what we're going to do in here. So again, these are all very recent models. Just a couple of months ago, this model called Delineate Anything came out, and it's an older architecture compared to like Segment Anything. It's a segmentation architecture known as YOLO, which means you only look once. But the advantage is that it's been trained specifically on satellite imagery and designed to predict these field boundaries, which is exactly the task I had in mind, right? So here, this model I don't think is on Hugging Face yet, but I did download the weights off of GitHub, and I'm just going to upload that to the plugin interface right there. So, and what's cool about these YOLO models is that they're computationally very fast. So instead of streaming this to the compute server, I'm actually going to just run this model locally on the CPU here. And then going to kick off inference, and just like the previous run, I'm going to you'll see the results come back. There's tiling happening in the background, and the actual front end is getting those segmentation results back, geo-rectifying them, and then displaying them. And here, already you can see this is a much better segmentation result than what we saw in the last two attempts, right? Again, it's not perfect. It misses some of these. Some of them you have overlapping masks, but at least I can start playing around with this and like with a very small number of manual tweaks, get something that's an actual segmentation result that I can start using for field delineation. So I think there are two takeaways. One is maybe unspoken, like use the right model for your task. But the second takeaway from like those last three examples that I showed you is that the plugin is completely agnostic to what the model type is and what the computational substrate is. We ran that same evaluation pipeline for GPT image 1, which we accessed through an API, and where the computation happened in a cloud-hosted serverless, windowless room somewhere. And we were able to do the same evaluation procedure for SAM3, which we sourced by searching Hugging Face, and to have the computation run on GPU. And the exact same workflow was supported for Delineate Anything, which we sourced the model weights from GitHub and downloaded them locally, and the actual computation happened in a local CPU. So it doesn't matter what type of model you have or where you're trying to run it. The evaluation that you can do in Anaximander is agnostic to both of those dimensions. And the way we implement that is to have this kind of client-server architecture. So this QGIS client is handling all the interfacing with the GUI, so all the doc elements, the status bar updates, the modals and things like that. But it's also managing user data. So when a model actually sourcing the data and tiles that you're sending to the model to do run inference on, but then it's also allowing you to define where to source models from, what a model definition looks like, and how to specify where to run that compute. And this only works because we have this companion server that either sits locally or remotely and will actually take care of the model loading, the device management, and also the data parallelism. And two things that I think are strong points of this architecture is that one is that it's front-end agnostic. So I'm showing you everything in QGIS because it's a good starting point for what to build. But you could code up a leaflet.js web app and it would talk to the server on the same protocol. And you could do all that orchestration in a web app instead. Same thing with Microsoft Planetary Computer, same thing with other GIS systems like ArcGIS. The other thing is about the other thing that was driving this kind of client server split is that this actually reflects the modern compute setups of a lot of partner organizations who are working on things like food security or biodiversity. GPU access is likely centralized in many environments. Like you probably aren't running this tool on a workstation with a GPU. There's probably a compute cluster somewhere in the organization where you send jobs to like a GPU queue. And this kind of allows you to deploy this companion server in that kind of setup. And then like we're also seeing serverless deployments of models becoming a lot more common. So something like Azure AI Foundry or those Azure ML workspaces, like the GPT image one deployment you saw was actually one of those. So you can like loop into these serverless deployments models pretty seamlessly. So that is kind of what the basic tool does. And from this kind of static demo, I'm going to talk about an actual case study where we're very, like, it's very early days in applying this tool, but it's already shown some pretty interesting and promising results. And the overall goal of this project is to create a crop type map of Kenya that indicates where maize is being grown. So maize obviously is an important staple crop in many diets across East Africa, but it's also commonly used as animal feed. So it's agriculturally and economically an extremely important crop. And being able to see at the end of the growing season where maize is being grown is extremely important for food security, economic development, environmental monitoring. It's definitely a multifaceted question. And the reason that the map is useful is that from a high resolution map, from the number of pixels that we say are maize growing pixels on the map, we can get the number of hectares. And then from the number of hectares of maize growing, we can try to estimate the yield and see how many tons or bushels of maize was actually grown in Kenya over the past growing season. The challenge is that the existing labels, so like agricultural surveys of which plots of land are actually maize or not, vary a lot in quality and applicability. So we've sourced a couple thousand, I would say like a handful of surveys of agricultural areas that try to mark in a geolocated way that, oh, this GPS coordinate is in the middle, or at least, if not in the middle, very near a field that's known to be maize, right? But what you can see is that the number of available labels differ in terms of their when they were collected. So some of the labels were collected way back in 2017, and some of them were collected in 2022. And why that temporal aspect matters is that since about 2020, Kenya, like East Africa in general, has been in a dry period, except for last year, where La Nina caused like a huge amount of rainfall. So qualitatively, the growing conditions in 2017 were very different than what they are in 2024 or 2025. The other kind of heterogeneity you see in label quality is that some data sets are very well documented and we can guarantee that they actually map out maize, but they might only be applicable to one county. Whereas other data sets that have a ton of labels might cover some of Kenya, but even though it's supposed to be like a Kenya-specific data set, it actually covers Tanzania or Uganda even better than it covers Kenya. So there's a huge amount of heterogeneity in like the usability of labels, but we've identified some data sets that have very high quality labels. Unfortunately, those data sets only have sometimes like 20 to 30 actual usable coordinates, but those 20 to 30 points are relatively high quality. So the idea is, what if we use this segmentation workflow that I've seen to not just look at the pixel that the reported coordinate falls into, but to select all the pixels in the delineated field that the high quality label falls into, and then sample from those polygons that represent the field, and then generate a lot more weak labels that way. So this is kind of what that workflow might look like in practice. So each of these blue dots with a white outline is a GPS coordinate from what we have judged to be a high quality label data set here. And you can see that they fall into, they usually fall right in the middle of a field. So let me see if I can segment some of these fields near some of these data points. And this is again using the delineate anything model that I showed you in the third example. Okay, so I think delineate anything did a pretty good job with these fields. Like most of the fields that have a marker in them got assigned to a polygon, and we can start using those polygons as a source of additional pixels. So I saw that it did well there. Let me kind of pan over to a different place where we have labeled data and see how well it does in generating masks there. And like these fields don't look that different from anything we were seeing before, but not quite as many of them are captured in this run of the model than it was before. So maybe I just need to be a little more zoomed in for running the segmentation. So here I can quickly do that. And then rerun the segmentation. If you were trying to do this in code, imagine how long it would take to like re-specify the center point of the coordinate that you want to sample imagery from, figure out the bounds, figure out the resolution and scale. And in this case, like, oh, for whatever reason, the model just can't pick up any fields because of in this particular region. But what I know about this data set is that if we have labels here and here, the sampling procedure for this data set was chosen in a way that nearby, these are probably also maze fields. So I'm going to run segmentation here, even though we don't have exact label support in these cases, because I know something about how the labels were sourced for the coordinates where I do have labels. And then segmentation is running here. And again, I get like a bunch more usable fields. So this process of this kind of iterative process is what I'm talking about when I say interactive orchestration and evaluation of these things. I mean, running kind of a preliminary test to see how well the model does here, and then maybe using the outputs of that test to see where else I should run the model. And if a model where the model outputs aren't behaving the way I want, I can pan, zoom, tilt, pinch, scan to see other modalities to say like, oh, what's going on here? But at the end of it, I've gone from like 5 to 10 strong labels to potentially hundreds of weak labels very quickly. And what we know from previous croptype mapping experiments is that being able to saturate a model with many weak labels that are derived from strong labels like this has a lot of benefits for downstream model performance. So this is kind of how we're actually using this in practice. I'm going to quickly move on to some challenges that we've looked into. So the first challenge is that, like the models that I've shown you are in some sense generic because their inputs and outputs are very well defined. So if a model spits out segmentation masks in exactly the same way, the system knows how to deal with them. If there's any kind of like bespoke output where you have segmentation masks in a slightly different format, then you're going to have to like probably write a specific adapter to plug that model into the system. The other thing that is also might be a challenge is bespoke inputs. So right now I've showed you how to basically pass one snapshot of the user's working window in QGIS through the model. But for really good models like the state of the art in field delineation uses imagery from 2 different data points to be able to understand the differences between the wet and dry season, for example. That's really hard to do in this GUI-driven setup. And then the final challenge has been like, I've shown you kind of an interactive version of a lot of these like model evaluations, but really how interactive this process is really driven by the number of cores. If you have a lot of GPUs that you can saturate with, then you can tile the entire viewport and get that inference done really fast. If you have like one old GPU and you're sending the tiles to it one by one, then you have a batch job, not something interactive. So the reason that this looks interactive is that we have a handful of GPUs to distribute our computation over. So that's kind of one challenge, but I think there's some interesting future work in that's in the pipeline. So I think that I've shown you how the tool supports segmentation workflows, but getting the object detection and the feature extraction workflows up to that same level of support is, I think, the first thing that we'd be working on to make sure that this is really addressing the most common needs of people working in GIS and ML. The next thing that I think needs some work is maybe the security story. So, when I was downloading the segment anything weights, I was basically telling the plugin to grab a 4 GB artifact off the internet and throw it onto a compute cluster. That's not a great security story. So moving to something that kind of containerizes these models and maybe like a formalized model registry where only certain models will be allowed to run, that I think would make this deploying this kind of model into an enterprise system a lot more feasible. And then the one that I'm more excited about is like integrating the backend, like an Anaximander server into agentic workflows. So instead, like if you can imagine one of these chatbot for maps interfaces, it might be relying on a generic vision language model like GPT Image 1 to do tasks like segmentation. But you can, like, now that we have the orchestration of picking a model with specific capabilities and handling where to deploy it, there's no reason that the orchestrator in this agent system couldn't realize, like, oh, this is a task that's better suited for a specialized model and delegate to that model instead of trying to use GPT Image 1's inbuilt image capabilities. So allowing orchestrators to delegate specific tasks to specific models is something that I think the Anaximander backend opens up. And I think that's like a pretty interesting area for exploration. So that's everything I have. I'd like to thank people who've been working on this with me in the AI for Good Lab. So I've been working very closely with Akram Zaytar and Girma Tedese. But of course, like, have been having a lot of really productive conversations with Gil Hashem, Mohammed Amish, and Tunu Lamai. The AI for Good Lab also has this incredible engineering team who's helped me set all this thing up, play with firewalls, understand Azure AI Foundry. And then again, I'd like to thank the MSR Africa team, particularly Stephanie and Wilson, for setting this seminar up and allowing me to talk about my work. So thanks again. I'll open it up for questions. And yeah.
Awesome. Thank you so much. Sajid, really enjoyed that. Do we have any questions in the room?
Yeah, I've got two questions.
Sure.
The first one is a bit. So, I'm not too familiar with GIS, but at least I understand polygons and stuff. So, the output from the models are polygons. So I'm guessing a polygon in a JSON representation format or something like
Right.
that. Yeah. So from the first images that you sent, you could go back to the first LGBT polygons that you brought. They seem to be a bit accurate, not really accurate, but they sort of follow the same shapes, even if they were not really exact that one, even though they are not really exact. So I'm wondering, is this something that could be corrected after in post-processing, or as part of an issue that we have with LLMs and generating structured outputs? There are things we call pedantic data models, where you build these data models. So you tell the LLM, this is how I want things to be, and add also some level of validation. If this happens, then you should correct it, or you should know there's an issue. Is this something that could happen within this tech?
Absolutely. So actually what's happening for GPT Image 1 specifically behind the scenes is that we're trying to do the image alignment by warping the input image, or the output image we get from GPT-1 and comparing it to the input image that we sent it. So we're looking for these like anchor points in the input image and output image and already trying to warp it. And like what you see here is like our best attempt to like do that alignment already.
Yeah.
So I think it is potentially possible. For the object detection case, I did look into having the model just spit out JSON. And I guess like in some very preliminary tests, I found that actually the image representation I got back, even if it wasn't polygonized yet, was more faithful to the object detection case than the JSON. So like the like the object detection like bounding boxes I got from BBC Image 1 were at least plausible. Whereas the kind of structured data, I mean, like the structure was right, but like the actual data inside was garbage. So yeah.
Yeah, the other one is you mentioned in the beginning about context.
Yes.
And actually, the visualization that you showed is something that I've always thought about.
Right.
So if there was a time I was looking at Palantir and what they were doing in Ukraine, and when you zoom in and then you zoom out, those two images are two completely different images, but they're images that could sort of give you context as to what is going on the ground, right? So I expected to see some sort of example when you're doing something close to that, but I'm not sure if you have something like that. But my question around this is, can you use these few shot context learning? So basically, you give it a bunch of, you see like how you did on the last photo, on the last video where you have, you're trying to get those bounding boxes on pre-labeled points.
Oh, right.
Yeah, it was some of the last part, on the last video. Yeah, you see how you were trying on this particular section,
right,
and then you move to a different section.
That's right, yeah.
So if you used sort of these images that are already pre-labeled, use them as the examples or rather the context so that you can sort of create weak labels on areas that are not mapped. Is this something that has been done? Is this something that you did?
Yeah, so actually like one of the advantages of segment anything, or claimed advantages of segment anything here is that you can use these like points as additional prompts. So like these are the geometric prompts I'm talking about.
Yeah.
And what I found like playing around in segment anything for kind of like well-defined features like buildings, like those prompts are like if you have like the centroid of a building delineated it, or like you know what that is, and then you pass that in as like a geometric prompt to something like segment anything, we'll get the building pretty well. It struggles a lot more with fields, and I think there's just like a lot more going on with like the kinds of input modalities that make field delineation harder. So like I mentioned, like state-of-the-art field models, they're using things like not just like data from multiple timestamps, but they're using data that's not in the like red, green, blue part of the spectrum, right? So it's using like near infrared or like images captured in different parts of the like electromagnetic spectrum that actually makes it happen. So like even though you can do these geometric prompts, and like that's something we actually support for SAM-style models in the plugin right now, it just takes a lot of tuning to get a usable field segmentation using this approach, in my experience. But things like building delineation seem to be a much better use case for this kinds of prompting.
Is this open source?
The whole plugin or SAM?
Yeah, the plugin. Yeah.
It's undergoing engineering review right now, and we're hoping to open source it soon. Yeah, of course. Yeah, yeah, sure.
So my question is about one of your last slides about the challenges that you faced. So one thing that I noticed is that there is different models coming around, and then you need to somehow load into your tool. How is difficult to, and how is like model agnostic?
You're right.
The tools so that you can, like, now you have these three, right? Like
right.
GPT, and you have SAM, and I forgot the other one.
Right.
So if new model come around, how is the model, is the tool going to? Do you need to go back and build again for this new model, or
right?
Is something that you thought about when building that?
Yes. So I think like there are kind of three stories for supporting novel architectures. One is maybe the architecture isn't that novel, and like what you're seeing in a lot of like remote sensing architectures is that you'll publish like weights for an existing architecture, but like those weights will be trained in different ways. So you might just be still iterating on a resonant, maybe a particularly deep resonant, but like how you get to those final weights are like that's actually where the innovation is happening. So if I have a resident class in PyTorch, I can just upload those weights to an existing class. And because of Torch Geo, which is one of the like open source tools that's like more on the code heavy axis, like it supports like hundreds of these architectures that are like commonly used. So like that's something that we bundled into what the architecture kind of like what the plugin kind of ships with. So like that's kind of story one, where just like even if there's like novel innovation happening, it's happening on top of architectures that are pretty well understood and supported. The second idea is that it kind of goes to this containerization or serverless deployment thing, where I've seen like some like really novel architectures like that require like really like pre-release builds of the Transformers library. They have like their own custom CUDA plugins or things like that. Instead of trying to deploy that, they'll just put it in a Docker container, and you'll serve the Docker container, and like the inputs and outputs of that container call are pretty well standardized. So you can, instead of like playing around with the actual weights, you just point it to somewhere you've deployed the Docker container, kind of like how GPT image 1 was deployed. And the third one is that you could actually like in the like I haven't like enabled it in any of the builds I've shown, but you can actually upload your own like PyTorch or own an X definition as well if you really wanted like absolute customizability. So along with the weights, you would upload the architecture, and then like the server would figure out how to run it through like an own X runtime.
So my second question is, show like a plot where you try to fit this tool into like something that accommodates both
right,
like GIS and them. So is it possible to like code in the tool, like if instead of only visualization, I want someone who is more into this side, right, doesn't want like have all these things.
Yeah, so like there's a way to get a Python, like an IPython terminal in QGIS. And as part of that, like the model definition would actually be automatically made available there. So you can actually inspect the model and see like the what like bytes are actually being passed in and out of the model. Or at least for local models. For remotely hosted models, it's a little trickier, but there is like some aspect of that. So I think it would be someone who's like figuring out like can use code to figure out the deployment story for a brand new cutting edge model, and then they want to play around with the outputs and like using the GUI. Like that's kind of like you could use like the Python console there, but I don't think we're quite at the level where we're mixing those two input modalities or input modes. Yeah.
Any more questions in the room or online? Awesome, thank you. I know Jill is on the call. I don't know if you'd like to say anything about any, future of the project, next steps.
Yes, can you hear me?
Yes, we can.
Yes, a great presentation by the way, Satish. So the work Satish has been doing is very critical for what the lab is focused on. One of the main subject is food security, and in many cases we are interested in croptype mapping for different purposes, right? For instance, if you want to estimate yield, let's say maize yield in Kenya, you want to be able to identify crop fields. So a critical aspect of it is being able to delineate, right, and to be able to say, okay, this field was mainly producing maize. This one is mainly producing maybe tea or coffee and so on. So you can have a clear estimate of different crop types across different regions. So yeah, I think we will be sharing more in the coming weeks about one of the, I would say, one of the largest initiatives when it comes to food security programs, and we are designing an upcoming program with a few partners. And yeah, happy to share that in the coming weeks, and looking forward to see also how this work particularly will be integrating will be integrated with other products that we are developing internally and also with other partners. Especially, you will notice that I don't know if we've talked about this before, but we have worked on several projects with Ministry of Agriculture, the Kenya Space Agency, and so on. And right now, we're trying to bring all this together into something that's, I would say, longer term vision to build a more sustainable products that could be helpful for Kenya and for the rest of Africa. Yeah, so let me stop here. We'll be sharing more in the coming weeks.
Awesome. Thank you. Thank you so much, Satej, for presenting. And yeah, thanks everyone for joining. Happy holidays, guys.
Yeah, happy holidays. Thank you. Oh,
Great presentation.
thank you.
Good presentation.
Thanks, appreciate it.
Yeah.